IBESS, Intro to Resources Part 2, focuses on two types of natural capital, renewable and non-renewable. As well, in this movie, we will examine the concept of sustainable use of resources. The harvest of resources in a sustainable manner must include full recovery of the ecosystem from which the resource was extracted, and no other degradation to the environment can occur. The significant ideas are: all systems can be viewed through the lens of sustainability. The renewability of natural capital has implications for its sustainable use, and sustainable development meets the needs of the present without compromising the ability of future generations to meet their own needs. Here is an outline of all the available movies for the Intro to Resources unit. Use this movie to find the movie you need for review. This movie is focused here. Natural resources are forms of wealth derived from nature. Natural capital is the storage or the stock. Capital is measured in mass per area terms. The forest is the storage or the stock. Natural income is a flow. It's the harvest, the yield that's taken from the capital. Natural income is what's used by people, exploited by people. And in this photo, the natural income is the harvest of timber from the forest, measured as a rate in mass per area per time terms. And the IB syllabus statement that kicks off Intro to Resources Part 2 is: define the terms renewable and non-renewable natural capital. You will need to be able to give examples of each. Here are definitions of the two classes of natural capital. Renewable natural capital would be living resources and some non-living resources, where the harvest can be less than or equal to replacement, resources that have a sustainable yield. For non-renewable natural capital, non-living resources that cannot be replenished within a time scale at all similar to the rate at which they are taken, the rate at which they are harvested. Renewable natural capital would be resources, living or non-living, that can be replaced in short periods of time. With careful management, rates of input, which are typically fast, can be equal to or greater than the rates of output. This forest is an example of renewable natural capital that can produce natural income in the form of goods or services. Here are examples of renewable natural capital, all living natural capital, that directly or indirectly depend on photosynthesis. The wheat field, the ocean fishery, the cattle population, and the cotton field are all renewable natural capital examples. From these storages, natural income can be derived. Cork is an example of living renewable natural capital. The bark on the trees is the capital, and the harvest of bark for wine stoppers or fishing buoys or flooring is the natural income as a good. Here are other examples of renewable natural capital, but in this case, non-living natural capital. Solar radiation is responsible for these examples of non-living natural capital: the river, the wind, and solar energy. Here are two more examples of non-living renewable natural capital: the stratospheric ozone layer and groundwater aquifers. In my view, we need to be careful with groundwater, and I've clarified groundwater by adding the adjective shallow. Only very shallow groundwater is renewable. Deep groundwater is not. The IB syllabus states that groundwater is renewable, but I don't fully agree. With living renewable natural capital, the rates of input are fast and the system can grow. When the rates of photosynthesis are greater than the rates of respiration, as you can see in the magnitude of these flows, the forest has a positive NPP. The positive NPP is new growth, and new growth, the lumber, can be harvested as natural income in the form of a good, the harvest of wood. Now, if the total output, respiration, and harvest does not exceed the input of photosynthetic growth, the forest can be maintained in a steady state equilibrium. The harvest of wood from the forest is thus a sustainable harvest. Some non-living forms of renewable natural capital, such as groundwater, have slow rates of input. Thus, their use requires careful management so that their use does not exceed natural replacement. If the rate of exploitation exceeds the rate of replacement, the system is not being managed sustainably. Here is a diagram showing the magnitude of inputs and outputs from a groundwater storage. You can see that the output is greater than the input. Thus, over time, the storage of groundwater will shrink. If this pattern of resource use continues over an extended period of time, the resource will disappear. This is an unsustainable use of groundwater. Here's a diagram showing the magnitude of inputs and outputs from a forest. You can see that the outputs are increasing through the year, thus the outputs are greater than the inputs. Over time, the storage will shrink. If this pattern of resource use continues over an extended period of time, the resource will disappear. This is an unsustainable use of the forest. In this diagram of a forest system, we can see steady-state equilibrium in the upper diagram as the photosynthetic input equals the outputs of respiration and the harvest of wood. But if the harvest of wood increases, the size of the storage will shrink. Remember, renewable resources can be used in an unsustainable manner if our management isn't careful. Before moving on to non-renewable natural capital, here is a table with examples of renewable natural capital. Now, this is not an exhaustive set of examples. Remember that groundwater and the stratospheric ozone layer are two examples of non-living renewable natural capital. Non-renewable natural capital is a term for resources that cannot be replaced at rates greater than the harvest. Input rates are extremely slow, if at all, and there's a finite supply. It's irreplaceable. It's replaced only over geologic timescales. You can see here there are no inputs, thus any extraction, seen here and here and here, shrinks the stock. Non-renewable natural capital includes all minerals: copper, gold, lithium, uranium, diamonds. Lithium is an example of a non-renewable natural resource. People extract lithium for batteries, as well as some medical uses. Uranium is a mineral. One must dig and dig to extract uranium from the deep earth. Uranium is a non-renewable resource harvested by people for use in nuclear energy production or military use. Soil is non-renewable natural capital. Replacement rates for a centimeter of soil runs into the thousands of years. Here is a table displaying examples of non-renewable natural capital. You can study this table on your own. Now, this table is not exhaustive. Spend some time with it. Notice the difference between storages and flows, capital, and natural income. Here is a diagram that you've seen before, and we can use it to illustrate the use of renewable and non-renewable resources. Which situation of the three below, these three, represents the use of a non-renewable resource, and which of the three situations represents the use of a renewable resource? Now, the only situation that represents non-renewable resource use is the middle diagram. Non-renewable resources are irreplaceable. The stock can do nothing other than shrink because the outputs are always greater than the inputs. Now, renewable resource use could be diagrammed by all three of these situations. Renewable resources can have smaller outputs than inputs, such that the system would grow. Fisheries can grow, forests can grow. Renewable resources can have rates of harvest equal to the rate of replacement, or renewable resources can be managed poorly, such that the rate of harvest exceeds rate of replacement. I've been dancing around the concept of sustainability, so here's the IB syllabus statement. Explain the concept of sustainability in terms of natural capital and natural income. Explain the relationship between natural capital, natural income, and sustainability. Sustainability is the use of a resource at a rate less than or equal to natural regeneration with minimal damage to the environment. Sustainability isn't all about balancing rates of harvest with rates of replacement. Sustainability must also include full ecosystem recovery from the extraction of resource, and no other environmental damage can be done in the transport or the use of the resource. And remember, sustainable use cannot apply to non-renewable resources. Here is a diagram of sustainable use of renewable solar-driven resources. The output is equal to the input. But let's specify some definitions for sustainability. It's the harvest of renewable resources at a rate less than or equal to the rate of replacement, a system that functions without a reduction in the natural capital over an extended period of time, the use of a resource without causing degradation of the environment or the natural capital due to transport or use of the resource. And remember that sustainable development meets the needs of the present without compromising the ability of future generations to meet their own needs. If you assume the stock is being managed by people, situation B, if it continues over time, is not sustainable. Here is a diagram of unsustainable resource use due to technology that has accelerated the output, accelerated the harvest to be greater than the natural rate of replacement. But if a managed system grows because the inputs are greater than the outputs, then the growth can be harvested, just the growth. And if this pattern repeats itself over and over, the system can be maintained in a steady state equilibrium. The harvest is called a yield and is, according to this diagram, sustainable. The harvest is equal to net production. The harvest is natural income from a renewable resource. So I've come back to definitions of the term sustainable, but on this slide, I'm emphasizing sustainable yield. Yield, the harvest. Sustainable yield is the highest rate at which a renewable resource can be harvested without reducing the stock, the natural capital, over time. Sustainable yield is the net biomass, total net biomass or energy, at time plus 1 minus the total net biomass or energy at time 0. So here's a diagram to display how sustainable yield can be calculated. It's the mass at time t plus 1 minus the mass at time t. This value, this difference between the mass at time t and the mass at time t plus 1, this is sustainable yield. Let's practice sustainable yield with a different question. Determine the net productivity and sustainable yield from the data given below. Be very clear about your units. Assume you have 160 snails and the total mass of the 160 snails is 245 grams. The snail's total mass increases from 245 to 285 grams over 20 days. Identify the natural capital and the natural income in this scenario and determine net productivity and sustainable yield from the data. Now you can stop the movie now or follow along with me. The growth of the snail population is 40 grams over 20 days. This is the net productivity and it is the sustainable yield. 40 grams over 20 days is the same as 2 grams per day. The population of snails is your natural capital, and the harvest of snails, 2 grams per day, is the natural income as a good. Calculate net productivity and sustainable yield from the forest given the data below. You can stop the movie now or follow along with me. At year 10, the mass of the forest is 8 times 10 to the 6th. 5 years earlier, the mass of the forest was 4 times 10 to the 6th. The difference, and this is the harvest, the difference between 8 times 10 to the 6th, 4 times 10 to the 6th, is 4 times 10 to the 6th kilograms over the 5 years, or 0.5 times 10 to the 6th kilograms per year. This is the net productivity and the sustainable yield from a renewable resource. Here's another question. Once again, the data is presented slightly differently. In the image, we can see fish in a pond with the mass of the entire fish population increasing from year 1 to year 2 and increasing from year 2 to year 3. Now, the sustainable yield calculated from year 1 to year 2 is 12 kilograms minus 4 kilograms, so that's 8 kilograms in the year. The sustainable yield from year 2 to year 3 is 32 kilograms minus 12 kilograms, or 20 kilograms in the year. You can see that the farmer of this fish pond has his or her maximum yield from year 2 to year 3. Sustainable yield is the highest rate at which a renewable resource can be harvested without reducing the stock over time. Another way to think of this is that sustainable yield is nothing more than the new growth over the time period. And keep in mind that definitions of sustainable resource use must include no damage to the environment due to extraction, transport, and use of the resource. So with that, here are the last IB syllabus statements of this movie. The impacts of extraction, transport, and processing of renewable capital may cause damage, making this natural capital unsustainable. Outline examples of how renewable and non-renewable natural capital has been mismanaged. Paper is theoretically a renewable natural resource, but are forests harvested in a sustainable manner? And how does the transportation of the lumber impact the environment? And how about processing? Here is a paper mill. The processing of paper does pollute the environment. The impacts of extraction, transport, and processing of renewable capital may cause environmental damage, making this natural capital unsustainable. Flowers are a renewable resource. Global cut flower sales approaches 14 billion per year, and most flowers are shipped from South America and Africa by air in special planes with refrigerators and well sprayed with pesticides. The impacts of extraction, transport, and processing of renewable capital may cause environmental damage, making this natural capital unsustainable. Biofuels are fuels distilled from plants, particularly sugarcane. As such, biofuels are theoretically a renewable resource. But in Brazil, the country with the largest biofuel industry in the world, forests are cut and replaced with sugarcane, as you can see in these images. The cane is distilled to produce the fuel, which is transported to cities to be available at the pumps. Given all of this, is biofuel a sustainable use of the resource? Has the ecosystem had a chance for full recovery? No. The original forest no longer stands, and in its place is agriculture, not for food, but for those wealthy enough to own cars, wealthy enough to buy fuel. The impacts of extraction, transport, and processing of a renewable resource may cause damage, making this natural capital unsustainable. Corn is harvested, transported, and processed into high fructose corn syrup, a product found in many of the processed foods we eat. The impacts of extraction, transport, and processing of a renewable resource may cause environmental damage, making renewable natural capital unsustainable. Lumber resulting from trees cut from forests is certainly a renewable resource, but are the forests replaced at the same rate of harvest? And what are the environmental impacts of transportation and processing? The impacts of extraction, transport, and processing of a renewable resource may cause damage, making this natural capital unsustainable. Ocean fisheries are quite depleted. The rate of harvest for numerous species has been greater than their rate of natural replacement. As well, when the nets are pulled in, numerous unwanted species, known as bycatch, are simply discarded. The impacts of extraction, transport, and processing of a renewable natural resource may cause damage, making this natural capital unsustainable. Ocean fisheries are declining if they're not already fully depleted. Humans have mismanaged ocean stocks. Large trawlers with massive nets are sweeping the ocean, harvesting fish at rates higher than their natural replacement rate. The percentage of global oceans fished has reached about 75%. But with fewer and fewer fish in the ocean, the relative catch per effort has gone down and down. Surface water running in rivers is a renewable resource, but is building a dam to hold water back good management or mismanagement of the resource? Dam building is controversial. Water is made available to farmers for irrigation, and the lakes behind the dam provide for recreation. As well, water flowing through the dam provides electricity. This is hydropower. But what of the ecological changes to the canyon? The lake behind the dam supports different species than would have lived in the original river. And consider all the water lost due to evaporation from the surface of the lake, water that would have otherwise have stayed within the river had the dam never been built. Have rainforests in equatorial regions been well managed or mismanaged? Have the trees been replaced at rates equal to the rates of harvest? Coal is a non-renewable resource. Here is a photo of a coal mine in China. Is the resource being managed well? Human societies burn more than 85 million barrels of oil every single day. Are human societies managing fossil fuels well? In this slide, there are two photos of a region in central Utah in the U.S. near the town of Hanksville. The area around Hanksville is government land. The region is dry and potentially beautiful with its dusty gray buttes. But off-road vehicle use is popular, and you can see the impact in the photo on the right. Has the government managed the land well? This slide reviews renewable natural resources. Review this slide on your own. Bring questions to class. Here is a review of non-renewable natural resources. Review this slide on your own. Remember the economic value of resources, where the natural income is a good, where the natural income is something harvested. That's easy to visualize. But natural capital has other values, particularly if the system is left intact, untouched. There are ecological or environmental values, the services that a system can provide. There is the aesthetic value, the cultural value in science or spirit. There's the technological value, and then there's the intrinsic value that ecosystems have the right to exist regardless of their benefit to humans. And then think about how we price resources. Is the resource worth more for its services or for its crop? And that brings us to the end of IB ESS Intro to Resources Part 2.